it's always a tremendous pleasure to be back at KITP in Santa Barbara. I'll pretty quickly jump into the setting directly from slide 1. So just very quickly. The microphone.
I think the microphone. Can we put it a little?
Yeah, of course. Yeah, I can do it. Yeah, sure. I'm generally a loud human being, so I'm always worried that it'll be too loud. Okay, folks can hear me in the back, right? Fantastic. So the story is broadly speaking about the search for topological phases, topological order in long-range interacting systems, a la the title of the conference. But maybe I'd like to start off with a little bit of a motivational perspective. In particular, I'd like to zoom into a particular experimental setting that I realize in the context of this audience needs no introduction. But just to get everyone on the same page, you already heard about this a little bit from Roger's talk on Monday, but nonetheless, in the last couple of years, there's been this remarkable platform that's been developed in the context of neutral atom optical tweezer arrays, where one can trap individual atoms using light and rearrange these atoms into essentially arbitrary geometries. So there's a square lattice over there, a triangular lattice, and a honeycomb lattice. And this ability to rearrange hundreds of neutral atoms into nearly arbitrary 2D geometries holds tremendous promise for being able to explore frustrated spin phases as new phases of matter, and that's the sort of broader context of this particular talk. But with this introduction and this setting that I think most folks are familiar with, I'd like to think a little bit about what people talk about when they emphasize the platform in terms of the novelty of the platform. And the thing that you often hear about is that the novelty of the platform, which is certainly true in my opinion, stems from the ability to rearrange, possibly in real time, as we might hear in Misha's talk in the afternoon, into arbitrary geometries. And of course, this ability to explore arbitrary geometries is very important for looking at frustrated magnetism. But maybe sort of paying homage to the title of the conference, I'd say that there's another novel ingredient that is not as often spoken about, but maybe fundamentally even more important in the context of frustrated magnetism. And my point is sort of that, well, of course, optical tweezer arrays allow one really tremendous flexibility in rearranging into arbitrary geometries, but in some sense, with some pain and some effort, my former colleague at Berkeley, Dan Stamperkern's group, is also able to, for example, make Kagame lattices or frustrated lattices optical lattices. So there's, in some sense, the geometry is much more flexible, and I think there are tremendous advances there, but it can also be realized in other platforms as well. On the other hand, I think the ingredient that is not as often said is that, in some sense, the fundamental Hamiltonians that emerge from this platform are really long range. And part of the emphasis of this talk is that that long range tail matters in the context of the types of topological phases and frustrated magnets that one can find. So I'll really dive right in and just start with this long-range context by emphasizing two of the kind of most natural encodings that one would imagine encoding a qubit or an effective spin degree of freedom in such a Rydberg tweezer array. And this perhaps slightly more conventional encoding of a spin, which again we might hear about in the afternoon and we've sort of already heard about on Monday, is using what's typically called a ground Rydberg encoding, where one encodes the spin down degree of freedom as the ground state, for example, a hyperfine state, and the spin up degree of freedom as a very, very highly excited Rydberg state. And then, owing to the nature of the blockade interaction, one naturally gets essentially the effective many-body Hamiltonian that describes the physics of this model is a long-range mixed field Ising model. So there's a long-range Ising interaction that goes as 1 over r to the 6th coming from van der Waals interactions. And there can also be a transverse field and a detuning which leads to a longitudinal field. So this type of a long-range mixed field Ising model, truthfully, I would never have guessed that there was a spin liquid phase in this particular Hamiltonian setting, but remarkable persistent advances on the theory side coming from Subir, Ashvin, Misha, Ruben Barrison and company, were able to demonstrate pretty conclusively that indeed for a specific lattice geometry, this quote-unquote Ruby lattice, and a specific deformation of that Ruby lattice within the broad parameter landscape of this long-range mixed field Ising model, there is a gapped Z2 spin liquid that is analogous to the toric code phase of matter. And it turns out there were beautiful experiments by Misha's group demonstrating the Z2 spin liquid, and sort of similar experiment or related experiments in the Google experiment looking at, again, this Z2 toric code phase. But the setting of this talk is not at all this ground Rydberg encoding. It's a slightly different encoding. And the encoding that I'd like to consider for the remainder of the talk is if one encodes the effective spin 1/2 degree of freedom, or the qubit, very simple, in just two Rydberg states that are allowed to interact with each other. So for example, the encoding that I'm considering here is some highly excited S state and some other highly excited P state. And in this type of encoding, the natural Hamiltonian that one gets out is also long-ranged. It's no longer a long-range mixed-field Ising model. Instead, it's a long-range dipolar exchange model. So the natural Hamiltonian is that this S and P state can simply have dipolar exchange, so flip-flop interactions of the form S plus S minus, and one has a 1/r³ tail coming from the fact that it's dipolar. I should emphasize, of course, that this type of Hamiltonian is also an extremely natural Hamiltonian for lattice trap polar molecules, at least in the absence of an electric field. With an electric field, you also have ZZ interactions. So the focus of the talk today will really be a question both theoretical, and I'll also show some preliminary, the if in Misha's introduction, preliminary experiments exploring some theoretical questions. Related to understanding the ground state phases of matter of this particular long-range Hamiltonian, which if we rewrite the S plus S minus term as an XX and a YY term, it's the dipolar XY model. And so one could very quickly immediately zoom into this question and ask, what is the ground state of the many-body ground state of this dipolar XY model? Note I've added an extra minus sign over here. Depending on the sign of J, of course, the answer can be either very, very easy or extremely difficult. When J is greater than 0, so there's an overall negative sign over here, then you have the ferromagnetic dipolar XY model. And the ferromagnetic dipolar XY model, as its name suggests, spins will want to align in the XY plane. You can have the breaking of this continuous symmetry that corresponds to rotations in the XY plane to form an XY ferromagnet. And because it's ferromagnetic, there are very nice techniques, even within analytic techniques within linear spin wave theory, to try to guess at properties of this low temperature XY ferromagnet, for example, what its dispersion relation are, and things like that. The setting for this talk, yes, Leo.
What controls the ZZ exchange?
Good. So the ZZ exchange, actually, there is a ZZ exchange that happens at next order in perturbation theory. So there are other Rydberg states around, and actually going up to one of those Rydberg states and coming down gives you another ZZ term that's sort of ZZ over r to the 6. So in fact, in this Hamiltonian, there is naturally, I didn't write it down, but there's another coefficient, let's call it J prime, ZZ over r to the 6. That J prime essentially can be controlled by some combination of the spacing between them, because one goes as 1/r³, one goes r to 6, and also some combination of which Rydberg state you choose, but it's kind of always there.
It's the same type as the first one you talked about.
It's the same type as the first one, exactly. There's an r, there's always that r to the 6, but this piece of the dipolar interaction can be stronger. That's right. It's not necessarily small, although the experiments that that I'll mention, that J prime term, the ratio of the nearest neighbor XY to the nearest neighbor ZZ, that nearest neighbor ZZ is about 0.02 relative to the nearest neighbor XY, and it only falls off stream. You can control it, you control it with spacing, because one, again, scales as 1/r³, one scales as 1/6, and you can also control it just via matrix elements by choosing which particular Rydberg state you use. Yeah, absolutely. But that's a good point. So the setting for this talk today is, in particular, what happens when one considers J less than 0, which leads to the anti-ferromagnetic version of the dipolar XY model. And we're just going to ask a very simple Hamiltonian question, which is, what are the many boundary ground states of this Hamiltonian in different lattice geometries? There are many different lattice geometries to choose from, and the ground state will, somewhat unsurprisingly, depend on the underlying lattice. And of course, even without long-range interactions, a short-range anti-ferromagnetic XY model on complicated geometries will be very difficult to analyze numerically or analytically, much less its long-range cousin. So one can ask, well, which 2D lattice should one consider? We've considered all of them. There are, according to Wikipedia, 11 natural Euclidean uniform tilings of the plane. And it turns out a little bit of cold water is that this particular dipolar antiferromagnetic XY Hamiltonian exhibits a symmetry-breaking ground state. So conventional order, symmetry-breaking order defined by a local order parameter on almost all of the lattices. I've put a question mark here on the triangular lattice. We don't know exactly what the answer is. It sort of seems like there's a collinear magnet that competes with the spin liquid there. But most of the setting for this talk will actually focus on the top right lattice, which is the Kagame lattice. Okay. I guess they're the list of Euclidean uniform time. I mean, you can consider others, but these were the ones that we considered.
These are periodic, right?
Periodic, exactly.
You can also consider quasi-periodic.
Sure. Yeah, if that's the setting of the question, absolutely, that's right. So, in particular, the method of attack for most of this talk will be a numerical study focused on IDMRG, the infinite density matrix or normalization group. And so that means that we have a translation invariant ansatz in one direction and a finite periodic boundary condition in the other direction. And it turns out that the first kind of setting for the spin liquid in this IDMRG is just seeing sort of the absence of symmetry breaking, which means that you should not see patterns forming in either the correlation functions or either the on-site correlation functions or the nearest neighbor correlation functions or any long-range correlation function. This plot is a pretty boring plot because all it shows is in principle that IDMRG finds the ground state to be reasonably featureless. There does not seem to be symmetry breaking at the level of collinear magnetism or the level of symmetry breaking. Instead, everything looks extremely uniform. Of course, it is totally fine to have correlations. It's just that those correlations can't break, for example, a translation symmetry or a spin rotation symmetry. In addition, although it's not shown here, it turns out that when one looks at the entanglement entropy of the ground state in IDMRG of such a dipolar XY model on the Kagame lattice, it's quite highly entangled and it does not break symmetry. So the evidence at the moment for a spin liquid phase of matter is quite simple, that we have a featureless, highly entangled phase. We can look at this both in IDMRG and on finite clusters, which again will be quite relevant for the experiments that I discuss a little bit later on. And within both of these contexts, we find up to boundary effects, relatively a featureless state at the level of correlation functions that exhibits quite a lot of entanglement when one looks at the entanglement entropy or the of the half system entanglement entropy. To zoom in just a little bit further and to try to understand what type of a spin liquid this is,
So, is it therefore understood why the different models applies in this?
Yes. Let me think about that for a second. Yeah, I think it is. I have to think about this. So the question is basically whether or not, if we see a featureless state, whether Lieb, Schultz, Madish, Oshikawa, Hastings applies, and whether we know that you either have to be, I guess, gapless or topological. And I think the answer is yes, but I remember there was some subtlety, because you have... Sorry, the subtlety is exactly the long-range interaction. Exactly, that's right. But I think, if you looked at the short-range counterpart, then in principle you have half spin per unit cell, and then LSM should apply in that case. That's exactly right. Good. Good question. So we have some numerical evidence for the fact that there is no spin rotation or spatial translation symmetry breaking, but it's natural to ask the question, can one zoom in a little bit further and understand what exactly the type of spin liquid it is? And it turns out that one natural probe, at least of whether or not the spin liquid is gapless or not, is to try to see whether or not there is a gapless point in the Brillouin zone. It turns out that given that we have a finite circumference in IDMRG, the natural momenta that are allowed don't cut through the full Brillouin zone. So a strategy numerically that's been employed quite a lot is to thread flux through the cylinder, the IDMRG cylinder, and all that allows in a super simple way, it's not complicated at all, is it allows one to shift the allowed momenta that one's sampling within the Brillouin zone. And what one finds, it turns out, is that it looks like as one shifts through this, that there's a diverging correlation length at a location that's consistent with where one would expect Dirac cones to be, or one would expect Dirac cones to be on the Kagame lattice. And in particular, we think that seeing these Dirac cones and the evidence of this at the sort of right Q and minus Q point lead to a Dirac cone spectrum that suggests that the spin liquid, the nature of the spin liquid, zoom in a little bit, is probably a gapless Dirac spin liquid. And just a super quick reminder, this won't be featured super strongly in the talk, this sort of Dirac spin liquid, this U1 spin liquid or this gapless spin liquid, we often think about in terms of the physical description as an example of quantum electrodynamics, which we are certainly familiar with in 3+1D, a 2+1 dimensional version of QED. And so there are fermionic spin-ons that see Dirac cones. So if one, for example, attempts to make a spin flip excitation in the Dirac spin liquid, that spin flip excitation, which naturally carries spin 1, should fractionalize into 2 spin-ons, each carrying spin 1/2. And those spin-ons should see a band structure that looks like a Dirac cone. There's a gapless U1 gauge field, which would be the two-dimensional analog of the photon, and because it's gapless, it is a quantum critical phase of matter. Yeah, please.
Yeah, 2 questions. One is, well, usually 2 plus 1 dimensional QED is defining. So, you think it's somehow stabilized by matter?
Yeah. So I think I'm not even. I think we're not even that far. So we're not. I mean, I guess. I think there, as far as I understand, there are still open questions about NF equals 4 fermions and just the stability of this Dirac spin liquid or this U1 spin liquid in general. And I don't know that I'm ever at sort of long enough distances or large enough wavelengths to test this confinement. I think there's this log confinement in 2D, right? Because you have the potential. So I'll sort of never, I don't know. I think the answer is sort of unknown. I'm not thinking about anything stabilizing it. And I'm just, we're never going to be at long enough distances to sort of be relevant in testing that log R confinement, I would say.
Question more specific is the dipole interaction crucial to what you
will? We will see in just a second. The answer is probably not, but yes, we'll answer that in just a question. Super good question. So this will exactly zoom in on Leo's question for just a second. So this Dirac spin liquid, you can ask a question, maybe the most natural question is, okay, there's a motivation from the experimental setting. This is the Hamiltonian that exists for Rydberg atoms in a particular geometry if one encodes spin a particular way. And that's a reasonable reason to explore. But one can ask a very natural question, which is this particular phase of matter the only, is long-range interactions or the dipole XY model the only way to get this particular phase of matter? I think the answer to that, Leo, is no. But zooming out even a little bit further, I'd like to remind folks just for 1 second that, forgetting about the Kitaev honeycomb model for 1 second, just thinking about isotropic interactions, so not bond-dependent interactions. As far as I'm aware, there are only 3 types of quantum spin liquids that have ever been found in either short or long-range interacting lattice models of spin 1/2 particles. And I believe those are a spin liquid, for example, that exhibits a gapped bulk and a gapped edge, the Z2 spin liquid, aka the Tor code. There exists spin liquids that have been found numerically, which are gapped in the bulk but gapless on the edge. For example, the chiral spin liquid, sort of the spinful analog of a fractional quantum Hall state. And also, there are states that are gapless in the bulk, spin liquids that are gapless in the bulk, and this would be the example of the Dirac spin liquid. So just for a setting of sort of, what are the types of topological phases in interacting spin 1/2 models without bond-dependent interactions that have been found in the literature, period. These are the 3 that have been found, although there's a huge zoo of more spin liquids that can exist in principle. And so, directly answer Leo's questions, one can ask thinking about this kind of zoology of spin liquids, one can ask, what is exactly the role of long-range interactions? Does it always lead to something new? Does it not? And I'd say there's a balance to that answer. So the context, for example, where maybe interacting spin 1/2 models is best studied is the Kagame-Heisenberg antiferromagnet, the nearest neighbor version of this. So if we imagine starting with this kind of classic starting point as a Hamiltonian starting point, people have studied for many years the S.S, the Heisenberg nearest neighbor antiferromagnetic interaction on the Kagame lattice, motivated by materials experiments, for example, in Herbert smithite. The original story from DMRG was that it might be a gapped Z2 spin liquid. There was maybe even some nascent evidence from neutron scattering that one was seeing a spin gap in Herbert smithite years ago. But more recently, careful studies from Mike Zalatel, Yin-Chin He, and others have kind of suggested that, in fact, it might be that this gaplessness the gaplessness of the system was not observed precisely because of this momentum issue that I was mentioning earlier, the fact that with a cylinder, you're only sampling a finite set of momenta. And so I think there's now competing evidence that indeed the ground state of this could be a Dirac spin liquid, although I'm not sure if the jury's out on either. So this is a little bit far away from our setting, which is the dipolar XY model, but one can get there with 2 perturbations. One perturbation is just by adding dipolarness. So you can imagine, for example, promoting this model to the dipolar Heisenberg model. And in this case, it's not immediately clear, but I would say that the long-range tail seems to maybe either maintain the Dirac spin liquid or maybe push this model into a chiral spin liquid phase, although I think the numerical jury is still out there. So in that sense, Leo, I would say, the long-range tail here, at least going along this direction, can, for example, maybe stabilize a slightly different topological phase than the original topological phase in the nearest neighbor case. The way to get to sort of the XY model, of course, another way is to now imagine taking the nearest neighbor Hamiltonian and simply perturbing by removing the ZZ piece of the interaction, so just going to the XX and YY piece. And as far as people have found numerically, again, another study from Yin Chen, it seems like there is no phase transition observed as one tunes from this to this. So the expectation is that whatever the phase of matter is here, it's probably the same phase here. So it could be a Dirac spin liquid as well. And then connecting this full story, the current work, which is focused, again, motivated a little by the experiments, but focused on this dipolar XY model, here we think it's a Dirac spin liquid as well. So in some sense, you might say that, there's a natural pathway to get from the Dirac spin liquid to the Dirac spin liquid otherwise. But you might also say that it's somewhat surprising that you could go dipolar and go to a chiral spin liquid and then go back and truncate the ZZ interaction and get to a Dirac spin liquid. So I think both perspectives are reasonable. Good. So with that, yeah, please.
Can't you say something from your viewpoint of view about the relevance of the term?
Of the long range, the relevance of the long range interactions. I think that okay. Right. I think, okay, so I haven't exactly, I suspect that the 1 over r cubed tail in 2D should be relevant. And I think that, sort of seeing that relevance, one can see that, at least as far as I understand, in fact, the phase of matter changes from the nearest neighbor to the 1 over r cubed case. But in general, it should be relevant, I think. Certainly, even from the perspective of long range order, it's relevant. So for example, there is Merman Wagner that says that, for example, one can't get continuous symmetry breaking at finite temperature in 2D with short range interactions. But it turns out for a power law, I think this will answer your question, for a power law that's 1 over r to the 4th or longer ranged, you can get finite temperature continuous symmetry breaking in a 2D magnet. So you can, I would probably guess in that case that maybe the 1 over r to the 4th, the power law being 1 over 4th, is the boundary between when it's RG relevant, when the long range interactions are RG relevant or not, although I'm not 100% sure. But certainly I'd expect 1 over r cubed to be relevant, because already I know that I can have finite temperature long range order in that case. Good.
I think it's marginal.
Is it marginal? I see. Okay. Really? But then I think 4 is marginal.
The Norman-Wagner theorem tells you it's applicable if the second moment of the interaction is finite. So 1 over r cubed times r squared is just logarithmic divergent, which means that's not applicable.
Yeah, but I think that's not, if I'm not mistaken.
Sorry guys, I wanted to say, can you wait that I bring you the microphone when you want to speak? These are going to make us lose 30 seconds, but I think it's going to be better.
So from what I remember, the Wagner theorem requires, in terms of short rangeness, that the second moment of the interaction is finite. So with 1 over r cubed, you basically have a logarithmic divergence, which is just a boundary between applicability and non-applicability.
I don't think, I see what you're saying. Somehow, I think that argument, I think about it, and I think I agree with that, and I've thought about it in the context of whether or not you should expect things like diffusion or transport questions. But I think, as Leo said, I think indeed it is for this ground state question, it is indeed, I think, correct me if I'm wrong, but I think it's where in 2D, it's 1 over r to the 4th. For 1D, I believe 1 over r cubed interactions already allow you to get 0 temperature continuous symmetry breaking, and then 1 over r squared allows you to get finite temperature continuous symmetry breaking. So maybe that's where the 1 over r cubed is coming. But I think 2D is 1 over r to the 4th, if I'm not mistaken. Is that right, Leo?
I may be misremembering, but I think it's d plus, if you characterize the exponent alpha as d plus sigma.
Yeah, exactly.
If sigma is bigger than 2, then it's short range.
Exactly.
But if sigma is less than 2, then
exactly.
And so in 2D, it's 4.
I think that's my recollection as well.
As the maximum expert probably in this talk. I may agree with Leo, but I would say that all of this is for ferromagnetic interaction. For the antiferromagnetic one, it is completely.
Sure.
So from the antiferromagnetic, you get a shift of D, because when you do the Fourier transform with the antiferromagnetic ground state, okay, this doesn't have an antiferromagnetic ground state, so but anyway, if it were a clean, if you do this on the square lattice with antiferromagnetic interactions, you will get a shift of D. So whatever it happens at sigma positive, it will happen sigma negative.
But remember, you've already started asking questions, so I get my full allotted time. Exactly. But I think, I think that's a very good point. So let me just go again. I think I agree with you. So I think in the ferromagnetic case, I know I'm right about 1/4, but in the antiferromagnetic, this is complicated because the long-range tail frustrates itself. So actually, I'm not 100% sure. But at least numerically, I think that it seems like I would guess that the 1/3 tail changes the phase of matter, but I mean, again, it sort of depends.
I think this comment is relevant because here what matters is not the behavior of the microscopic Hamiltonian. It's really, let's assume the conformal field theory corresponding to the direct spin liquid exists. Then we ask, depending on the scaling dimensions of those operators, whether this non-energy interaction is relevant or not. The answer depends on the scaling dimensions.
I see. Okay. I guess, and I'm not sure even the scaling dimensions are precisely known from conformal bootstrap. But okay. Let's continue for a sec. So, okay, with this long-range story sort of in play, let me now switch the setting a little bit to focusing on how one might try, given that it was experimentally motivated, how one might try to actually prepare the state, observe the state, and then tell you about some preliminary experiments. This is, I think, pretty fun. So perhaps the most natural route to preparation one might think about is very much related to the way that Misha's group explored the Z2 spin liquid. One can imagine that maybe the simplest thing to do is to apply a transverse, or in this case, in the plane, X magnetic field. And for very, very large omega over here, this would correspond to, in experimental terms, a driving between the S and P states. And for very large omega, the state is obviously just everything aligned in the X-axis, just a paramagnet. And you can imagine that then ramping down in a time-dependent fashion, omega would be able to lead to exploring whatever the ground state of this dipolar XY model is. It turns out that it is true that at sufficiently large omega, the phase is everything aligned in the X direction. But it turns out that as one decreases, as one decreases omega, it turns out that one goes through, slide this shift a little down, goes through a series of phase transitions, in particular to different intervening solid phases, the 1/3 phase, the 1/6 phase. So this is, rather than a possible route to preparation, I would say a rather impossible route to preparation, because one goes through many different phase transitions. Another route that one could imagine is slightly more complicated because it requires spatial dependencies, but another route that one can imagine is using what we call a glider perturbation, where in this case we imagine applying a transverse field in the Z direction, but has strength that is either positive or negative, so it wants the spins to align against or with, depending on whether the sites are red or blue. So remember, ultimately, I should have mentioned this earlier, the Dirac spin liquid emerges in the SZ total equals 0 sector, so the all half up, half down sector. And to be able to have an initial state that is in that half up, half down sector, this type of a pattern for the initial state has to double the unit cell. So you'll have 2 reds, 1 blue here, 2 blue, 1 red, and all that corresponds to is that the 2 reds have a magnetic field pointed up, the blue has a magnetic field pointed down, the 2 blues have a magnetic field pointed down, and the spins in my initial state are just aligned along their field direction. And it turns out that this staggered field experimentally can be produced by a Stark shift using local light field. And one very nice thing one can immediately check, unsurprisingly, is that if one does IDMRG on the Hamiltonian that contains that perturbation for large delta, you see a ground state that is indeed the sort of paramagnet corresponding to spins aligned in the right direction. And for the delta equals 0 case, you have the DSL. And it turns out, as far as we can tell, that these are smoothly connected with respect to each other by changing the strength of delta. So here is showing the order parameter, or not even order, but the staggered polarization and the entanglement entropy, and it looks like there isn't this situation where one has many, many different phase transitions before one goes from the paramagnetic state to the spin liquid state. So that seems like a reasonable route for preparation. And if we have this reasonable route, maybe another natural question just to keep in the back of our heads is, what exactly would be the right methodology to detect this? And of course, one has access in these types of platforms to different things than one has access to in the solid state. So as opposed to looking at spin transport or neutron scattering, one has direct access, for example, to lots of real space correlations in a single shot. And so I just emphasized two very, very quick ways to spot a Dirac spin liquid in the sense of providing evidence beyond just the fact that you don't see symmetry breaking. So one way is a story that I think many of you will be familiar with related to graphene. It turns out that you'll remember that for graphene, where the electrons see Dirac cones, depending on whether or not the termination of the edge is armchair or zigzag, there is or is not an edge mode. So for example, in the zigzag termination, there's an edge mode between the Dirac cones, and in the armchair edge mode, in the armchair termination, there is no edge mode. So you can naturally ask a question, which is, if you think the emergent spin-on degrees of freedom, so if you think the emergent spin-on degrees of freedom above the ground state Dirac spin liquid should see a Dirac cone, is there a similar analogy for the Kagame lattice, which is, are different edge terminations going to show edge modes or not? And indeed, we think that might well be the case. So there's a particularly spiky termination, which looks like it should have edge modes. These are all free fermion calculations at the moment. A particular spiky edge termination should have edge modes, and it turns out if you have an excess spin-on, a hexagon edge should not have edge states. And the way we kind of made this excess spin-on is very simple. We just simply worked with an odd lattice geometry where now you always have one extra spin degree of freedom, and that one extra spin degree of freedom has to mean that there's at least two spin-ons in the problem. And the question here is just, do they localize to the edge or not? You'd expect that if the edge is gapless, that on a finite size system, maybe that gapless means that the lowest energy states for the spin-on are indeed at the edge. So in addition to the free fermion calculations, you can do some reasonable DMRG calculations. This is now full many-body calculations of the ground state, where you imagine taking, for example, as I promised, an odd number of lattice sites with either the spiky termination or the hexagon termination. I'm not sure it's the most amazing evidence. It's hard to get to big enough system sizes to say something, but it seems like the spin-on, at least the density, is somewhat localized around the edge. It was hard to get things symmetric, so the hole is sort of a little bit closer to the left and the right, but you can see that for the spiky termination, as kind of beautifully predicted in the free fermion calculation, the excess red spin-on is localized on the edge, whereas for the hexagon termination, it looks like at least the edge doesn't seem to have most of the excess spin-on weight. So that could be one way that would be very natural in a quantum simulation platform like a tweezer array to be able to look for this by simply removing one site from the tweezer. Another thing that's equally natural at some level is to look at Friedel oscillations. We're used to thinking about Friedel in metals. One thing you can do for the Dirac spin liquid is when you prepare it, you can imagine trying to prepare it in the presence of a little perturbation at a single site. Scattering from that perturbation will lead to Friedel oscillations, and the Friedel oscillations will in particular know about the wave vector between the two Dirac cones if they exist, and that should lead to particular peaks in your Brillouin zone if you look at the Fourier transform of a spin-spin correlation function. So just very natural. There are two very natural things that would be extremely hard to do in the solid state, but taking out a site or adding an extra local perturbation are things that one can naturally do in these real space type experiments. So just a few last quick minutes, I'll show some experiments. So indeed, this has been a super fun collaboration with Antoine Brauwis's group in Paris. They have such a Rydberg tweezer array, which implements the anti-ferromagnetic dipolar XY model. And what they do is indeed, they use Stark shifts, local Stark shifts, to apply this type of an HZ Hamiltonian. And they use the same local Stark shifts to be able to arrange things. And they start with this large delta. And after some of those large delta, they then decrease delta as a function of time, and they hope that adiabatically that the state will follow towards the ground state. And at the end, this is now experimental data, what they find is indeed that it seems like a lot of the initial population has become a little bit more uniform, although certainly there are still correlations that haven't fully gone away in this finite size system. So without going into too much detail, here's a little bit of a time-dependent picture for how the correlations disappear for this, I think it's 80 or 90 site atomic lattice, where they're really ramping down the delta Z field as a function of time. And just as a very, very quick interlude, numerically, one thing that we found as we were ramping down this delta field, this initial paramagnetic field adiabatically tuned, we found that there was a particular intermediate valence bond solid that happens on the edge. And we could look at this valence bond solid as a function of this delta, and you can see that some bonds were more antiferromagnetic or ferromagnetic than other bonds. And it turns out very nicely in the experiment, although the magnitudes are not the same, they start actually from this side. So delta's large here, delta's large here. And they see indeed that they can see at intermediate delta the formation of this valence bond solid. And ultimately, at the smallest delta, they see that they come back together, as you have to be for the Dirac spin liquid. Otherwise, there'd be some sort of symmetry breaking pattern. So we were honestly quite excited at that moment. We saw this for both ZZ and XX correlations, that maybe since we were preparing this intermediate valence bond solid extremely well or reasonably well in the experiment, that maybe at the end of the experiment, we were indeed getting to a featureless Dirac spin liquid state. We also ran some experiments with them where they did some there and back experiments. So they would ramp into the Dirac spin liquid and then back. And you can see that theoretically we expect to almost get quite a bit of the population back from the initial configuration. They see again similar things in the experiment. And now one can ask the question, which is the if in Misha's introduction. Of course, the most important couple of slides is it a coherent Dirac spin liquid? And the honest answer is I don't know. In the sense that we looked with them at these other positive signatures. So is there a dependence on the edge termination? And we didn't see anything in that case. And what we think might be happening is that there's very, very subtle effects coming from the fact that in their simulator, there's still positional disorder coming from the fact that actually the atoms are not trapped when they do the experiments. There's a little bit of disorder in the DSL in terms of the location of the tweezers in the first place. And it turns out that positional disorder, any spin liquid, the Dirac spin liquid in particular, is extremely sensitive to that. But they've put in some efforts. So after the little bit of cold water, I'll give a tiny bit of warm water. It'll be 3 slides and I'll end. And the tiny bit of warm water is that they've now gone back and pairwise tried to optimize the interactions to make them as uniform as possible to limit the positional disorder, which would correspond to interaction disorder in the Hamiltonian. And in that setting, they've now tried a really pretty experiment where they attempt to adiabatically prepare the Dirac spin liquid, but they have one particular Z field, one particular Zeeman field that's still on. So you're preparing the Dirac spin liquid in the presence of this excess perturbation on a single site and looking for Friedel oscillations. So again, for a free fermion calculation, this would be the signature of scattering at the vector between Q and minus Q. And they've now, very preliminary, done an experiment on 114 atoms. And when one Fourier transforms the spin correlation functions and looks at the same regime of the Brillouin zone with a mother's loving eye, one can somewhat see that at least it does not look like there may be extra amplitude in this picture at the right locations where one expects to see the Friedel oscillations. Let me end there and just acknowledge the work was done, especially on the DSL side, by Marcus Vince and Vincent Liu, who are graduate students in the group, Johannes Hauschild. And actually, I didn't get to tell a story about a chiral spin liquid in the same Hamiltonian, but luckily Francisco Machado is somewhere around, so you're more than welcome to talk to him. The experiments were a collaboration with Antoine Brows's group, and all of this work was with my good friend Mike Salata. Thanks.
Thank you for the beautiful talk. I'm just puzzled. How is that possible that you go from a product state to a spin liquid without crossing? So it looks like very smooth in your state preparation. What's the?
There has to be a phase transition. We think it's probably, at least the evidence that we have is it's probably a second order phase transition. So things can look smooth. And of course, one lesson that I learned from Misha in particular is that in finite size systems, all adiabatic ramps will be smooth at some level.
Unless you have a first order.
Unless you have a first order transition, exactly. So in a second order transition with a finite size gap, you should expect, it's not so crazy that actually things look quite smooth.
Okay. So, thank you, Norma, for a wonderful talk. So I wanted to ask a question / comment on the role of long-range interactions, because I sometimes do not understand when we say that long-range interactions are details is frustrated, Because, okay, on the Kagome, of course, but I mean, on a regular, on a like square lattice, I don't see this frustration because it's always true that antiferromagnetic nearest neighbor wins overall, no? Because those couplings are, so this is a classical arrangement, of course. So what I mean to say is that if I take nearest neighbor antiferromagnet on the triangular lattice, I see frustration not really at the classical level. While for long-range interaction on a square lattice, the classical level it's unfrustrated. The states are close, of course, but so do you think that this can be an argument to say that long-range interactions are not so important, and so you can take the route that you were depicting, like in this four square?
Yeah, I mean, truthfully, I think there isn't probably a good universal answer. So maybe let me make a couple of statements. There's just various cases, proof by example. So I know, for example, that 1 over r cubed ferromagnets in 2D, the dispersion changes. 1 over r cubed on the square lattice, as you were saying. 1 over r cubed antiferromagnet square lattice, the dispersion doesn't change. No effect whatsoever. It's just dominated by that piece. And then I also know of examples where, in principle, adding the long-range tail, for example, in Kagame, does indeed, or yeah, it's not exactly clear on the triangle lattice, but you can imagine that it sort of does add extra constraints. But whether or not the integrated weight of those constraints will ultimately matter relative to the nearest neighbor order that wants to form, that's kind of a very, very microscopic question. And actually, I have no good intuition for whether or not there is like a universal principle. Bipartite lattices with long-range tails shouldn't matter, but frustrated lattices should. I don't know that that's very easy to answer.
But anyway, you expect that the long-range tails on the Kagome alters the dispersion relation?
This is a dangerous statement to make. So I think that, at least for the Heisenberg interaction, I think it's not crazy that the long-range interactions maybe lead to a different phase, although even there, I think the numerics, I think some stuff that Francisco has done, it's unclear whether or not that's exactly the case. But at least going from nearest neighbor XY to dipolar XY, I don't think the long-range tail in the Kagame lattice changes the phase of matter. But again, whether that's like a universal statement, I just can't, I don't want to make a guess on it.
Thank you very much for the excellent talk. This may be related to Nicolo's question, but so you commented on the 1 over R6 van der Waals interaction. In the last decade, there's been a lot of work showing that if you do pairwise versus many-body dispersion effects in 2D materials, you get much more accurate predictions. So this is much beyond the kind of system sizes you're looking at. But those electronic fluctuations that are mediated at long range, they can sometimes transition from 1 over R6. If you sum all n-body interactions, you can go to 1 over R5, 1 over R4, and even beyond in certain geometries. And this has been shown in many types of 2D materials, molecular included. Can you comment a little bit on how these, you commented a little bit on the 1 over R4, but how many body van der Waals, or sort of in larger geometries, you might see these long-range electronic fluctuations that become impactful in these spin liquids?
Okay, so let me make sure I understand. So the question is basically, when you say many body interactions, you mean a parallel interaction, interaction, but like three spin interactions,
4, 5,
4,
6,
5, 6,
all
exactly.
summed, yeah.
Okay, so I can tell you a setting where I think it's interesting. I don't know that anyone's really explored models except kind of taking states and then going back to parent Hamiltonians. But it turns out, I think that for non-abelian spin liquids, non-abelian chiral spin liquids, often one finds that if one takes kind of the wave function and goes back to the parent Hamiltonian, that parent Hamiltonian has like non-pairwise many body interactions in that sense. I don't know whether or not, thinking this way, I just don't know. I mean, I think physically, I mean, I can imagine basically like thinking about pairwise interactions and going higher order and thinking about a many body sort of version of that. Mm-hmm. But I think what you're saying is actually there are settings where microscopically you just get n-body interactions with long-range interactions. It just seems interesting to me. It seems like it might be able to maybe stabilize things that are non-abelian, which we haven't really seen except for the Kitaev honeycomb model. But yeah, I don't know. It's hard for me to understand exactly. I mean, if you really have extensive body interactions, then I don't exactly know how to even normalize things. I would venture to guess that if you have the same power law tail, but you have like many body interactions that have like n particles interacting, that almost feels like kind of a mean field all-to-all interaction, and then everything's just dominated by that term of the Hamiltonian. So that might be the sense in which those many body terms become more important than the pairwise two body terms, but I'm not 100% sure.
And is this related to Nicola's question about the long tails and the spin liquid?
No.
No.
As far as I can tell, no. Because Nicola's interested in just saying like two body terms, like, if you take two spins far away, like what exactly is frustrated about this? We say that, well, this dude wants to be, correlated, this dude wants to be anti-correlated, and he's wondering about, that tail, integrating that tail in the antiferromagnet, how that compares to the nearest neighbor effect. But if you're worried, you're interested in the case where you have many body, like multi-spin interactions that are also parallel. So it's a slightly different setting.
Thank you.
So Norm, hey, so related to the first question about the preparation, so do you have a guess for how the preparation time scales with the system size? I mean, I guess it relates to the gap. Do you know something about it?
Yeah, no. So we've tried to play with that a little bit, but we sort of expect that it should somehow be a polynomial, but we don't exactly know what that polynomial
Linear,
should be.
quadratic? Yeah.
It's hard to tell. It's hard to tell. It's actually hard to tell because it seems like there's like almost no effect at some level. So it's not so much that if quadratic or linear, it's like even getting to seeing sort of whether it's linear at all.
Well, next speaker is setting up. So what did you see in this data that indicates something non-trivial?
Yeah, so I think the evidence was just that, what they did was basically, the question is basically whether or not you indeed, so having a pattern sort of the Fourier transform of the spectral function, basically, that has extra weight at these particular points corresponds to scattering between the two Dirac cones on a Kagame lattice. And all I was pointing out was that when they tried to do this experiment, this is data actually, they put an excess Zeeman field here, and they ramp down and prepare in the presence of this, and they look at the Fourier transform. You can subtract this from the case where they don't have this, and in that case, you basically see that there is this kind of trapezoid of weight at these points that correspond to where you'd expect the kind of 2kF scattering between the Dirac cones to be.
But it's some kind of pattern, it's a spatial pattern.
Exactly, but that's expected. So let's just be super clear. In space, so if you have generally any critical phase, right, you expect correlations to decay as a power law, and that power law is a critical exponent of the theory. It turns out that for the Dirac spin liquid, what you expect is that it does decay as a power law, but it also has an oscillation on top of that decay. And that oscillation, the wave vector of that is specifically the wave vector between the two Dirac cones. And so it is indeed, you're trying to see whether or not that wave vector exists in that data. Exactly. Sorry.
All right. Okay. So let's thank Norm again. So the next